Hello everyone, welcome to our final project presentation. Today we are going to show you something that can actually help save people's eyesight, and we built it using deep learning. This project is called EVIT-DR, which stands for Efficient Vision Transformer for Diabetic Retinopathy. By the end of this video, you will see exactly how it works, how to run it on your own machine, and what kind of result it produces. And we team as a team we created the project with the team of Krantikiran G and with myself, Balsa Iswar Reddy and Rupavati, under the guidance of N. Sai Kiran, Assistant Professor, Department of CSM. What are you looking at? Is a fully working web application that takes a retinal photograph, a fundus image, and within seconds tell you whether the patient has diabetic retinopathy and how severe it is. It also known as where in the eye it detected the problem. Let's start with our problem we are trying to solve. Diabetes is one of the most common diseases in the world. One of its most serious complications is diabetic retinopathy, a condition where high blood sugar slowly damages the vessels in the retina at the back of the eye. The dangerous part, it has no symptoms in the early stages. By the time the patient notices their vision is getting blurry, significant and the often irreversible damage has already been done. Currently, diagnosing DR requires a trained ophthalmologist to manually examine retinal photographs. This process is slow, expensive, and simply not available in many parts of the world, especially in rural and under-resourced areas. There are five stages of diabetic retinopathy: no DR, mild, moderate, severe, and proliferative DR, which is the most dangerous, where abnormal new blood vessels grow and can cause complete vision loss. Our system detects and classifies all five of these grades automatically. So the question is, can we use AI to automate this screening process and make it fast, accurate, and accessible? This is exactly what the EVIT-DR does. Our solution and architecture. Our solution is a hybrid architecture, deep learning model that combines two powerful architectures, a vision net and a vision transformer, in a single pipeline. Here is how it works. We take a fundus photograph and resize it to 224 by 224 pixels. This image goes through two parallel branches simultaneously. The first branch is vision net B0, a convolutional neural network. This is excellent at detecting local features like micronutrients and exudates. These are the tiny abnormalities that indicate DR at different stages. The second branch is our custom vision transformer. It splits the image into small patches, encode their positions, and use attention mechanisms to understand global relationships across the entire retina. Things like the pattern of blood vessel distribution. The features from both branches are then concatenated into 512-dimensional vector, passed through dropout layer, and normalized for regularization, and finally through a fully connected layer that outputs probabilities for all five DR grades. The combination gives the best of both worlds: local detail from CNN and global context from the transformer, and the result is 97% precision, 97% recall, and 0.99 AUC scores on our test set. Software usage. Let's walk through the how to set this on your own machine. This should take 5 to 10 minutes. First, we have to sure you have Python 3.9 or 3.10 install, which means TensorFlow 2 works best with these versions. You can check by typing Python version in your terminal. Next, you have to download the project folder inside your system. So these files you will see: ultimate.py. Templates are indexed in the inside of templates folder. We have index.html file, and next front end, at the front end requirements.txt. We have the requirements of all a flask where they try transfer flow of open CV and etc. Best model.h5, this is the model file. Best model.h5, this is the model file. Here the app ultimate.py is the backend. This is the folder structure highlight in each file as I mentioned. Now let's create a virtual environment so our package do not conflict with anything else on your system. You have to follow the commands of Python /m and when script activates for Windows, source when bin activate for Linux or Mac. These will be you can found in our readme.txt file. Once the virtual environment is activated, install all required packages using the single command pip install /r requirements.txt. This is for to install the requirements in txt file to download. This will install the Flask, TensorFlow, OpenCV, Pillow, Matplotlib and everything else in the app needs. It may take a couple of minutes depending on your internet speed. The last thing you need is the best model.h5, this file. This is the trained model around 200 to 400 megabytes. Place it directly in the project root folder, the same folder as app ultimate.py. Without this file, the app will start but won't be able to make predictions. We can walk through the source code. Here it is. Here is the app ultimate.py in VS Code. At the top we defined two here. At the top we defined two custom layers, patches and patch encoders. Patches layer and patch encoder. The patches layer takes the input from image and splits into two small space titles. Patch encoders then add here patch encoder. Patch encoder then add learnable positional information to each patch so the transformer knows where each patch is in the image. These two classes are required to load model correctly when we call tf.character.model.load model when we pass the custom objects. Otherwise, TensorFlow won't know that to how to deal with highlights of load model. Here we have to def load model. This is to load our model. This function calls with the custom objects parameter. And next the get diagram heat map. Roots handles single image analysis. It accepts a file upload, processing the image, runs prediction, generates the gradcam overlay and returns everything as a JSON response. The predictor class all confidence scores the original image and the heat map, all encoded as base 64 strings that the front end display directly. The batch predictor is the gradcam overlay. And next we have this predict method and this is batch predict. Roots handles multiple images in one go. The front end sends all the files together under a key files and the back end returns an array of results, one per image. This is our index.html, means our main front-end code. The end front end is in a single HTML file. The JavaScript makes a post request and our Flask backend or post API waits for the response and then updates the page showing the side-by-side image comparison and the probability chart dynamically without any page reload. Now for the most exciting part, let's run the application and test its live. Python, we have to, if we want to run, we have to deal with command prompt. Here we have to run our main backend file, Python app ultimate.py. Here you would see Here you should see an model loaded and the server starting at port 5000. The model is loaded to the server is running. Let's open the browser and go to localhost 5000. Here you can see it is running in 5000. Here we can see that it is localhost 5000. It's running in here. You can reload it once. This is the complete web entrance. You can scroll through and see how it works section, the 5 great place explanation, and the model architecture diagram and the performance visualizations. And let's reach to the detection. You can go to the detection. Scroll to the text section. Make sure that single image is selected. You have to select a single image. We'll click the upload card and select a retinal fundus photograph. I'm using a sample image from the test set. Let's take a fifth number. Here it is. The moment you upload the image, the app immediately shows it on the left the starting processing, and you can see it says analyzing, and while the backend runs the interface and generates gradual heat map. And here the result. On the left side is the original fundus photograph. On the right is the gray gradient overlay. The warm red and yellow regions show exactly which part of the retina the model look at when making its decision. Below we have the predicted grade confidence. Badge, and below that the fully probability distribution across all 5 classes. Here it is. The model is not just giving us a label, it's showing its reasoning. This is what makes it trustworthy and useful in a clinical context. Here we can see about live batch processing. We can taste a text from image here. EVIT-DR also supports batch processing, which is important for real-world screening scenarios where you might need to analyze dozens of images at once. Click the batch. Switch to batch mode. Now click the upload card and select images control or CMD to select several images at once. We are using control. Select all images. You can see a progress bar tracking the processing of images once completed. Result appears with a grid of cards. Each card shows the thumbnail, the predicted gear, and the confidence bar. At the top, the summary bar, which total of how many images fall into each grade across the entire batch. This gives a clinician or screening operator an immediate overview of the patient color. Now we can go to the performance results. Here we can see the proliferative DR, mild, severe, no DR, and no DR. Here are the examples. Here is the performance visualizations. This is the confusion matrix. This is the confusion matrix for our test set. You can see the strong diagonal dominance, meaning the model is correctly classifying the vast majority of the images in every class. The few miscalculations that do occur tend to be between adjusted severity levels, which is clinically understandable since mild and moderate cases can have overlapping features. You can see it. So the classification card. This is the TSN plot. It takes the 512 dimensional feature, embedding our model learn and them down, projects them down to 2-dimensional. You can see 5 well separated clusters, one for each DR grid. This tells us the model has genuinely learned to distinguish between the classes, not just memorized patterns. So the class. And here is the classification report showing per class precision, recall, F1 and F1 score. All classes are at above 0.95 with the overall macro of F1 of 0.97 and IVC curve of 0.9, and these are very strong results for the 5-class medical imaging task. And we can conclude here, and acknowledgements are to summarize. The EVIT-DR is a complete end-to-end system for automated diabetic retinopathy screening. It combines the local feature detection of efficient with the global attention of vision transformer, achieves 97% accuracy, and provides gradcam explainability, so users can understand and verify every prediction. The full source code and training notebook and installation instructions are all documented in the README file. The app can be run locally within a single Python command or deployed to cloud using the included proc file. Here is the proc file we provided. Here it is. We believe tools like this can genuinely make a difference, helping in screen more patients faster, catching DR earlier, and ultimately preventing avoidable blindness in communities that don't have easy access to specialist ophthalmologists. Thank you for watching. If you are having any questions, please feel to ask. We are happy to talk through any part of the code or the model is more detailed. And here is our title, EVIT-DR.